Thank you very much, Justin, and thanks to everyone for this opportunity to talk briefly about the NEXUS project, a collaboration between RMIT University and DST. I'm Matt Duckham, so I'm one of the leads on the NEXUS project, together with a number of other researchers here today, and I'll come to acknowledgements, the wider team at the end. But getting to the core of it, NEXUS is really all about demonstrating practical and flexible approaches to combined high and low level fusion of spatiotemporal data. So NEXUS is itself a system of systems that can combine a wide range of different reasoning tools and techniques, including statistical and probabilistic and logical approaches. But unifying these different components is a rigorous approach to uncertainty, and also an understanding the need to support explanations about how the system arrived at particular conclusion. So I think we've made some excellent progress across a range of areas in NEXUS, but in this brief time, I'm just going to highlight 2 or 3 specific areas of where I think we've made advances. This slide shows the evolution of the NEXUS architecture. And what I want to do is just linger for a moment on this, the current high-level architecture, because it really shows our system of systems approach. At the core of NEXUS is really an array of different reasoning components, as I say, both statistical and logical, and all embedded in a distributed streaming architecture. So the idea is we can support many different data streams coming in, and then we construct the workflows from combinations of reasoning components that can assist with a wide range of intelligence tasks, identifying anomalies and patterns and predictions, effectively making sense of these data streams. And of course, ultimately, these reasoning outputs need to connect to a wide range of different decision support and user interfaces. And to enable that, we really use semantic web technologies that not only describe the data outputs from NEXUS and help query that output, but also describe and query information about the reasoning processes themselves to help support explanations of system outputs. So here are just some of the reasoning components and fusion workflows that we've been developing under this NEXUS architecture. And I'm going to just briefly give a little more detail of 1 or 2 of those, in particular, the streaming probabilistic qualitative spatial reasoning workflow, SPQSR. And then also I'll talk a little bit about some of the detection of trajectory manipulation that we've been working on, and particularly highlighting some of the explanation supports that we developed to support those outputs. So diving into a little more detail, one of these important advances for NEXUS has been the development for the first time of a consistent approach to probabilistic qualitative spatial reasoning. And I think perhaps the next speaker, Yuan Fang, may also talk a little bit about this area. And in fact, the advances I'm going to talk about are described in a paper currently under review at the International Journal of Approximate Reasoning. So we can perhaps give a little more detail to anyone who's interested in that. But in essence, we've combined a range of existing established spatial logics, such as Allen's temporal algebra, region algebra, RCC, RCC5 and 8, cardinal direction calculus, and other logics that may be familiar to people who already know about spatiotemporal reasoning. And we've combined that with Markov logic networks that effectively allows us to handle uncertain and soft evidence. So, for example, a cardinal direction calculus, CDC, this is a typical spatial logic that allows us to reason about qualitative, imprecise knowledge about directions. So, for example, if we know, let's say from analysis of a social media feed, that the island labeled here F1 is south of a vessel O1, and that a vessel of interest O2 is southeast of F1, then CDC, cardinal direction calculus, allows us to infer that O2 is in fact also southeast of O1. Now, what our extension allows us to do is to really start to reason with soft evidence, where, for example, perhaps we're only 90% sure that F1 is south of O1, and perhaps even less sure that O2 is southeast of F1. And in the paper, we really show in detail in a range of increasingly sophisticated scenarios how this can work and how it can help support spatial reasoning. But I highlight this is just one of the kind of important high-level spatial data fusion workflows that we've been developing with. Other reasoning workflows include things like movement anomaly detection, and as I said before, detection of manipulation of AIS, marine identification tracking trajectories, which I'll come back to shortly. But that does bring me to this other important feature of the NEXUS approach, which is that alongside all of these different reasoning components and fusion workflows, we need the ability to explain the reasoning steps and effectively support why queries. Why did our system suggest this action or this output? And in fact, we've got another paper under review for the moment for a special issue, a journal special issue on explainable AI, which details like our approach to this problem too. So, I think I might be able to share that as well. And the approach here is really based on semantic web technologies and connecting established upper level ontologies to domain-specific ontologies that help us reason and talk about particular areas where our system is working. Here's one specific illustration of how that ontological approach works for reasoning about AIS and vessel trajectories. We have a number of different reasoning components that we've developed that help spot manipulation in vessel trajectories in AIS and shipping data, and we can use them individually or in combination. We can connect them up into workflows, but to do that we need a common language to describe our knowledge. And some of that common knowledge is provided by ontologies. On the left here, on the blue, we've got elements from the simple event model, which may be familiar to people who've worked in this area a bit. And that enables us to be consistent in how we talk about times and places and vessels we are tracking, as well as the events that those vessels are involved in, like meetings and the movements that are happening. And we can also describe the provenance of our information and of the reasoning outputs themselves, in this case using the Provo ontology in Lilac, which again may be familiar to some people here. So a particular inference or process in our system can be described using this ontological approach using Provo. And the sort of linchpin of all of this is the events themselves, like meetings between vessels or particular movements, anomalous movements of vessels, which are both events, and they're also outputs, reasoning outputs, data entities in terms of Provo. So we've implemented NEXUS. I also want to highlight that a key part of NEXUS is pulling together all sorts of different components and getting them working together as much as developing kind of new components ourselves. We've implemented it as part of a working system. We have a number of different case studies we've been using, such as in particular illegal fishing, which I've sort of been pointing towards in some of the examples so far. But the key thing is that NEXUS is integrated. It is working with DST's own decision support architecture. It's designed to fit with the streaming architecture. We, everything's implemented as containers in Docker. And so this is actually just a little video of all it requires to get started with NEXUS. You essentially have to specify the different reasoning components, connect them up to each other and the different data streams, and then you're away. You can let it process data as it comes in real time, and then generate the outputs that are needed for for further intelligence outcomes. And what's happening next? Well, we're certainly in the next 6 months. We're very much looking to develop further user interfaces so that we can actually showcase, taking decisions based on this data. I've actually just got here a really simple user interface we developed in a couple of days to be able to show some of these outputs. And the idea here is that the streaming AIS data is being monitored for a range of different potential manipulations, a kind of evidence of different manipulation. And we've got individual detectors as well as a Bayesian network combining different outputs from different detectors. And we can really quite simply, make that data, the outputs of those reasoning available, highlight, alerts when new reasoning outputs come in, and also, show some of that on, for example, maps, so you can actually see where these things are happening. So that's really all that I wanted to say, except to end by thanking and acknowledging the really big team that's behind this. My co-CIs at RMIT. We've had been very lucky to support some incredibly talented postdoctoral researchers through this project, and absolutely, shout out to DST collaborators, in particular Jonathan Legg. But we've had superb support, and I'm really looking forward to that continuing. Thanks, everyone.